Hi, this lesson is about the limit of a function. So here's the notation. This is read as the limit as x approaches a of f of x equals L. So a limit exists when you take the limit of a function and it equals a finite number, L being the finite number. And what that means is that the closer the values of x get to a, on both sides of a, both from the left side and the right side of a, the closer f of x gets to a value that we're calling L. And it could get close to L, or it could possibly equal L. Both scenarios would mean that the limit exists. So here are 4 different scenarios regarding limits. So the first one says that the limit as x approaches a of f of x equals L, and the function at a is also equal to L. So this is an example of where the limit value and then function value are the same. The next scenario is that the limit equals L, but the function does not exist at a. Third scenario is the limit as x approaches a of f of x equals L, but the function value has a different value than L. So the function exists, but it's just not the limit value. And then finally, the limit doesn't exist. And there's a few different ways that this last scenario could happen. So here's a little bit more vocabulary and understanding of what limits are before we do some examples. So when considering the limit of a function from only one side, that means either the left side or the right side, we call those one-sided limits. So this one, the notation here, where we have the limit as x approaches a, and then you have a negative sign next to it, this means a from the left side of a. So if you can imagine a graph, let's say some function, f of x, and if we have a value a, because a will be some value of the independent variable, and f of x is your y, or your dependent variable. So the left side of a is this side. So this would be the left side of a. So values less than a. And then values greater than a would be the right side of a. And that notation is when you have a little plus sign next to it. So that's the limit of f of x as x approaches a from the right. So you can say that a limit of a function exists at a only when the left-hand limit and the right-hand limit have the same value. So this is your definition of a limit. If you're trying to prove if a limit exists, you want to show that you get the same value whether you approach a from the left or you approach a from the right, and they both converge to the same value that we're calling L. If they have 2 different values from the left and the right, then the limit at a would not exist. Okay, so here are some scenarios examples of the scenarios above. So the first scenario was the limit as x approaches a of f of x equals L, and f of a also equals L. So here's a graphical example. So suppose you want to evaluate the limit as x approaches 2. Well, as I get closer to 2 on the left side and the right side of 2, when I say close, I mean like within a decimal from 2, or 100th of a decimal, so very, very close to 2, then you can see that your function value is approaching this value up here, which corresponds with the number 3. So your limit value is 3. But since this is a graph without any holes or asymptotes, you can see that f of 2 is also equal to 3. So this is an example of where the limit value and the function value are the same as you get at 2 and as you get closer to 2. Okay, here's another example of scenario 1, where the limit value and the function value are the same. And we're going to look at this from a numerical perspective. So numerically, that means that we're actually going to plug in values that are close to 1, right? Because that's what your limit is approaching. And so these are values close to 1 that are to the left of 1, less than 1. And you can see I get closer and closer. I go from 0.9 to 0.99 to 0.999. And the y values are here, right? You plug that into your function, and it looks like your numbers your y values are getting smaller and smaller, because negative 0.19 is definitely greater than what you see here, negative 0.001999. And then if I do the same thing as I get closer and closer to 1 on the right, so I have the furthest one here, 1.1, and then I get closer and closer, 1.001 is closer to 1. And so you can see here that again, your y values go from 0.21 to 0.002001. So it appears that as my values of x are getting closer to 1, my limit value is 0. But then you could also check it. What is f of 1? That means you would plug in 1 squared into the function and you would also get 0. So it's another example of where your limit value and your function value are the same. So this is reading it off of a graph in this first example, and this is a numerical analysis of the limit where you're actually plugging in values to the left and right of your limit value into your function to determine what the behavior of the function is. Okay, scenario number 2. That's where your limit value is 1, is some value that we're calling L, but the function does not exist. So those are often or always going to be graphs with holes in your graph, like you see in this picture. So as I get closer and closer to 3, which is what we're trying to analyze here, so I'm on the left side of 3 and on the right side of 3, and if I follow the path of the graph, as I get closer and closer to 3 on the left and on the right, your function is getting closer and closer to that open circle which corresponds with a y value of 4. So that means that you can say, as I get closer and closer to 3, the limit value is 4, because the graph is getting really close to 4. But if I were to say, what is f of 3, you can clearly say it is undefined because the open circle means it's not a defined point on the graph. So if this was colored in, then it would be like scenario 1, where f of 3 is also 4 and your limit value is the same. But because it's open, you can say that f of 3 is undefined. So in other words, 3 is not in the domain, and yet the limit exists. And so again, if we look at this through a numerical analysis of this, here I have a rational function. So we have the limit as x approaches 1 of x squared minus 1 over x minus 1. So if you were to plug in 1 into this function, well, you would get 0 over 0, which we know means it's undefined. So the function does not exist at 1. That's a restriction on the domain. But that doesn't mean that you can't evaluate a limit. So again, here I have a couple of examples. 2 numbers close to 1 that are less than 1, and 2 numbers that are close to 1 but are greater than 1. So this would be the left-hand limit, this is the left-hand limit, and this would be the right-hand limit. So if I plug these x values into my y value, you get the values here in this column. And so you can see as you get closer and closer to 1 for x, it looks like your y value is getting closer and closer to 2. So the limit value is 2, although the function is not defined. Okay, here's another example. Scenario 3 is when your limit exists and your function exists, but they're not the same. So this is one example. If I evaluate the limit as x approaches 1 and I read this graph, when you get closer and closer to 1 on the left side and the right side of 1, and you follow the path of this graph, so on the left side, it's getting closer to that open circle. On the right side, it's also getting closer to that open circle. That open circle corresponds with a y value of -3. But if I were to evaluate f of 1, like where is the function defined at 1, you can see that it's this point here. So f of 1 is equal to 2, but the limit value is -3. Remember, the limit is the behavior of the function, or the y value, when you get close to this number that the limit is approaching. So it doesn't have to equal it. When you're evaluating a function, it's when it's equal to 1, what is the y value? So they are different in this case. Okay, so that was a graphical explanation. Let's look at this numerically. So here I have a piecewise function. I want to evaluate the limit as x approaches 1 of g of x, given that g of x is equal to this rational function when x is not equal to 1. And that one should look familiar. It's an example I used a couple minutes ago. And it's got a value of 3 when x equals 1. All right, so we already did this one numerically a few minutes ago. We found that as you get closer and closer to 1, this limit of the rational function is 2. But you can see that when x is 1, g of 1 is actually equal to 3. And here I've drawn the picture so that you can see it. As you get closer and closer to 1 on the left and the right, your graph, if you follow the path, is going toward that open circle. That's the one with a value of 2, but the function is the closed point above it up here at 3. Okay, and now we're on to scenario number 4. Scenario number 4 is when the limit does not exist. Okay, so the limit does not exist for two main reasons, either because the limit is approaching plus or minus infinity. And remember, the limit has to approach a finite number. So plus or minus infinity is not a finite number. Or the left and right hand limit are different, meaning it doesn't satisfy the definition of the limit, which was above in the box. So here's an example of one that does not exist. So I have my function, which is 1 over x squared. The graph looks like this. And if I evaluate the limit as x approaches 0, as I get closer and closer to 0, if you follow the path, on both sides of this graph, it's going towards infinity. So my limit value is going towards infinity. That's a good thing to know in order to understand the behavior of functions, but it is not a limit. It is not a limit that exists. In addition, here's an example of one where with two different limits. I have this h of t equal to 0 if t is less than or equal to 0, and 1 if t is greater than 1. So this is called the Heap side function, and it represents a light switch. So this one would be off, and this one would be on. Okay, so as you approach your limit for as t approaches 0 from the left, that means less than 0, then it's got a function value of 0. But if you this should be a 0 here. But if you approach the limit from the right of h of t, well, on the right side of 0, values greater than 0, that has a value of 1. So when your left and right hand limit are not equal, you can say that the limit does not exist. And then I have a picture there above. The less than or equal to 0 part is here. It's a constant. Greater than 0 is here. Again, another constant of 1. And so you can see visually that as you get closer and closer to the value of 0 for t, your function is going in two different places, either 0 or 1. So you can say that the limit as t approaches 0 of h of t does not exist. D and E for does not exist. All right, so a really convenient way to evaluate limits is by something called direct substitution. But you can't use it in every scenario. So when can you use direct substitution? So if A is in the domain of f of x, and you want to evaluate the limit as x approaches a of f of x, well, that will just equal f of a. So instead of using that numerical technique where you're plugging in a lot of numbers to the left and right of a into your function to estimate what the value of the limit is, this replaces that. It's really just plugging in the value of a directly into your function, and that only if a is in the domain. So if it's undefined at a, you will not be able to do that. So let's look at some examples. So here we have the limit as x approaches, this should be an x, not a t. We need the same variable throughout. So as x approaches -2 of the square root of 5 plus x squared. All right, so this happens to be a radical with no restrictions on the domain. So any value of x would result in a positive result inside of the radical. So no worries here, -2 is in the domain. So that means you can plug it in directly into the function. So that then you have the square root of 5 plus -2 squared. So that's 5 plus 4, which is 9. So therefore your limit value is equal to 3. So this is much more convenient than, for example, plugging in numbers to the left and right of -2 into this function in order to guess what the limit value is. So you get the exact value as long as you can apply direct substitution. All right, so here we want to sketch the graph and evaluate the following limits. So I've given you a piecewise function. I have a linear function here, x minus 4 for x less than -2. I have this parabola, x squared minus 1, for values of x between -2 and 2, but including -2, since -2 is less than or equal to x, which is less than 2, and then another linear function for values of x greater than or equal to 2. All right, so in order to graph this, you really have to pay attention to the values of x where it is defined. So here's the x minus 4 part. You want to substitute in -2 in here. That gives you -6. And then plug in, for example, -3. You need an open circle at -2, -6, which is down here because it's less than -2. And then connect the points going downward left. Then we have our parabola. You want to plot that between -2 and 2. Make sure you have an open circle at 2. So that's what you see here. So at 2, the value of y is 3. I have my vertex here below. And then connect those points. And then when you plot 2x, make sure you start with 2. Pick a number greater than 2, such as 3. Connect the 2 points, and here we get our 2x part of the graph. All right, so now that we have a visual, we're going to evaluate our limits. So the limit as x approaches -2 from the left. Okay, so that means you're looking at this part of the graph or this part of the graph. Since that's a linear function, you can apply direct substitution. Under normal circumstances, x minus 4 has no restrictions on domain. So by direct substitution, you get that the limit value is -6, which, by the way, is that open circle right there. So that's your limit value from the left of -2. Now, if I'm interested in my limit value when I'm on the right of -2, that means you need to pay attention to the parabola. And again, parabolas have no restrictions on the domain. You can plug in -2 into the quadratic, and so you get -2 squared minus 1, you get a value of 3. So basically, you can safely say that this limit at -2 does not exist because they're different on the left and on the right. Now let's look at +2. If I'm interested in determining the value of +2 from the left, that's what this notation means. That means, again, you have to plug it into the parabola, okay, because that's where x is less than 2. Left of 2 is less than 2. So plug it in, you get another value of 3. And then we need to look at the limit value from 2 on the right. And on the right, that's going to be for values of x greater than 2. So that's this one. Again, by direct substitution, you get a value of 4. Okay. So here we're going to evaluate the limit from the left and the right of this function, 3 over x minus 5. Okay, so and that's as x approaches 5. So we know that at 5, this rational function is undefined. because it would be 3 divided by 0. The graph looks like this. We have a vertical asymptote at 5. And so as you get closer and closer to 5 on the left, you can see that your graph here in blue is approaching negative infinity. And as you get closer and closer to 5 on the right side of 5 and look at the path of the blue curve, that's approaching positive infinity. So not only does this limit not exist, but on the left and the right side of 5, it has different behavior. And again, knowing that is helpful in order to graph functions later on. You could also do this numerically. You can plug in a number like 4.99999, or as close as you want, and plug that in. And the more nines you attach to that 4.9, the closer you are to 5, the more negative your number results in. And that's how we get the negative infinity. And you can also try a number like 5.0001, plug that in on the right, and you'll see that the number just keeps getting larger and larger. So you can do that numerically with your calculator just to get more comfortable with what the behavior of the functions are. All right, so here we have an absolute value function. We want to show that the limit as t approaches 7 of t minus 7 over the absolute value of t minus 7 does not exist. So in order to prove that something does not exist, either the limit has to be going to infinity or negative infinity, or the limit on the right and left side of, in this case, 7 has to be different. All right, with absolute values, you definitely need to work these a little bit different. I cannot apply direct substitution. I can't plug in 7 in here because then I'll get 0 over 0, and we know that's undefined. But we need to be able to prove that the limit does not exist. Okay. As I approach 7 from the left, I want you to consider what the absolute value is doing to this expression. An absolute value changes a negative to a positive. 0 always stays as 0, and a positive doesn't change. So if I get a positive result inside of the absolute value has no function at all. But if I get a negative inside of the absolute value, it changes the sign to positive. So when I'm on the left side of 7, let's say like 6.9, and I plug that in here, 6.9 minus 7 is a negative number. And that negative number changes to positive because of the absolute value. So a way to rewrite this without an absolute value is to leave the numerator alone, but write the denominator as the opposite of t minus 7, no absolute value in what I circled here. And the opposite of a negative number is a positive number. So this function does the same thing as the absolute value function when you are on the left side of 7. But by doing that, you can then treat this as just an algebraic expression. These two cancel, and you get a value of negative 1. So your limit value on the left is negative 1. Now, if I look at this limit from the right side of 7, let's say something like 7.1. If I were to substitute 7.1 in here, inside of my absolute value, it's a positive number. And when it's positive, the absolute value doesn't do anything to the expression. So you can actually rewrite this like this, and it means the same thing when you're on the right side of 7. So again, you can then simplify this algebraically. They both cancel, so you get that the limit on the right is 1. So since the left-hand limit and the right-hand limit are not equal, then you can safely say that the limit does not exist. Okay, here's another one with another absolute value. There's a little bit more to it. We're going to evaluate the right-hand limit and the left-hand limit of the absolute value of 3 minus x over x squared minus 9. Okay, so let's look at the right-hand one first. All right, so if I'm on the right side of 3, let's say like 3.1. If you were to plug in 3.1 in here, what's inside the absolute value? 3 minus 3.1 is negative. The absolute value changes it to positive. So that same function is performed by taking the opposite sign of a negative result. It also makes it positive. Okay, but notice that this denominator is factorable. So I factored it. It's the difference of perfect squares. Okay, so I can almost do something with it, except the signs don't really match up. So if I distribute this negative here, the x turns to positive, the 3 turns to negative, and I'm left with x minus 3 over x plus 3 times x minus 3. These cancel. So now I'm left with 1 over x plus 3. Once I cancel in this line, it means that I can now apply direct substitution. And when I plug in the 3 in for x, I get 1 over 6 as your limit value from the right. All right, so let's see what happens on the left. All right, if I'm on the left side of 3, like something like 2.9, if you were to plug in 2.9 in here, 3 minus 2.9 is a positive number. Taking the absolute value doesn't change anything. So on the left side of 3, I can rewrite this without the absolute value, and they're still equal. And I also factored the denominator. But again, I can't exactly cancel anything because the numerator is off by a sign. So I factored a negative 1 out of the numerator. Now the x minus 3's cancel. So I'm left with negative 1 on top over x plus 3. Then by direct substitution, plug in the 3. You get that the limit value on the left has a value of negative 1/6. So again, if you were asked, does the limit exist at 3? Your answer would be no, because the left and right hand limit are not the same value. Okay, so let's look at these common graphs that you should be familiar with. Suppose you had to evaluate the limit as x approaches 0 from the right of ln of x. Right, so it is helpful to know the graph of ln of x. It looks like this. Natural log is only defined for positive real numbers. So would it make sense for you to look at the limit from the left of 0? It doesn't exist to the left of 0. But on the right of 0, as you get closer and closer to the origin here, you can see that the path is going towards negative infinity. So it's another graph where the limit of the function does not exist at 0 from the right, and the function value does not exist there either. Here's another one. We want to evaluate the limit as theta approaches pi over 2 from the left and from the right for tangent of theta. So tangent is another graph you should be familiar with. So we're interested in pi over 2. So there is an asymptote at pi over 2, as well as negative pi over 2 and 3 pi over 2. But we're really interested in what's happening on the left side of pi over 2 and on the right side of pi over 2. So on the left side, you can see that your function is going towards infinity, but on the right side of pi over 2, it is going towards negative infinity. So it's again another example of a limit that does not exist, but again, knowing the behavior helps us understand the graph. Okay, here's another one. We want to evaluate the limit as theta approaches pi over 6 of 4 sine of 2 theta. All right, sine and cosine have no restrictions on domain. So theta could be any number. So that means I can apply direct substitution. So by direct substitution, you plug in the pi over 6 in here, which is what you see in this line. Notice that every time you apply direct substitution, you no longer write this limit symbol. So it's no longer written once you plug in by direct substitution. So be careful with notation. It's important in math. So here, the 2 and the pi over 6, the 6 cancel. So you're taking the sine of pi over 3. Remember, pi over 3 is 60 degrees. It's one of those special triangles that you should know. So pi over 3 is 60 degrees. That means I have 30 here, 90 here. This is root 3, this is 1, and this is 2. So the sine is opposite over hypotenuse, so that's why we have 4 times root 3 over 2. Simplify the 2 and the 4, and your limit value is 2 root 3. Right, so that's it for that lesson. Give the homework a try. Good luck.